right. So good afternoon, everybody. So welcome to this is going to be the first session on GeoEvent Server at the Dev Summit 2017. So our IoT session has been running, I think this is the third time, I believe, yes, at the Dev Summit. Today we're going to have three presenters. Myself is Morakot Pilouk. I've been with Esri for more than 20 years now, working in the capacity and the roles of senior software developer, and also doing consulting for projects. The second presenter will be Ming Zhao. He's been here longer than me. So he's going to take the role of lead developer for GeoEvent in 2017. The third one would be Joyner. He has been our product engineer, but he's going to start taking the role of product manager in a few months from now. So the outline of the topic for today, we're going to talk about Internet of Things, trends and landscape in the IoT space, then move on to the applications and markets, kind of look into where we're heading in IoT for the next few years. Then we're going to talk about real-time GIS and IoT. Then talk about the GeoEvent Server specifically for IoT. The last section will be collecting and storing IoT data. So although our topic is about GeoEvent for IoT, but we would like to present it in the context of real-time GIS and the Internet of Things. So you could see from the background maps on this slide, the world maps composed of many things. And we're going to see how those things are going to be related to real-time GIS. So what's the IoT? A number of people have asked. So the definition that a number of people try to put together, network of physical objects embedded with electronics, software, sensors, and network connectivities. So this is not the only definition that you can find out in the internet. Someone can give you different definitions. There are many kinds of physical objects that can be part of the Internet of Things. This slide can only give you some ideas, just a small subset of things. Important thing is these objects have to become connected with internet and become online so we can communicate with them. So today, apart from this slide, we're going to have 5 demos. So I'm going to give one simple one, and to these two gentlemen will give us others. So we look at the adoption rate of the devices, IoT devices. So this is counted by 100 people. The OECD, which is an organization that did these data collections and statistics in 2015. So this chart probably not big enough for you to see, kind of showing if you walk down the street, pass by 100 people, how many devices might be online comparing to the number of people. So look at a little bit more clear, simplified chart. So we see the South Korea is top of the chart. Not surprisingly, because South Korea has been one of the world leaders in producing IoT devices. So on the chart, you probably notice that India and China are probably pretty low on the ranking, but that's just because they have a lot more people. And this chart is not the indication of how advanced are they in terms of technologies. So look at the trends, how this IoT has been developed in the past. Around the year 2000, we start seeing devices like RFID tags, that if you notice, when someone tries to walk out the door from the shopping mall, sometimes they get a loud beep. And that's because there is an RFID reader and an RFID tag work together. And the RFID tag is attached to merchandise or the item people bought from the mall, the shopping mall. Perhaps that RFID tag hasn't been erased or demagnetized. So when someone tries to walk out the door without demagnetizing the RFID, the reader will pick it up and then send out the alarm. Since then, the IoT has been developing mostly in the surveillance, security, healthcare. And then around this time, we start to see a lot of devices, sensors coming out. And those coming out with very affordable price. The sensor may only cost a few dollars or even cents. So people start packing a lot of sensors into devices. The advancement in terms of locations, GPS, try to pinpoint where are you on the earth, or even indoor, getting really accurate now. And also some other technique, not just GPS from satellite. Technique like using magnetic fields from the building structures, try to pinpoint you with the magnetic patterns, also become available, can tell you pretty accurately where are you in the buildings. So let's go back to that. Sorry. We start seeing that devices start to get smarter, and there are a lot of on-edge data collections and also real-time analytics on the device as well. In the near future, we expect to see cross-device communication and analytics. So this is this slide shows some sample of microcontroller and chips that has become available. These are microcontroller boards that provide interfaces to sensors, whether it be analog or digital. Computer getting really small, even on stick, like what you see the Intel computer stick that run Windows 10. So you can connect that stick to an HDMI monitor or big screen, and that's your personal computer right there. So other credit card size computer, you start seeing like Arduino, Intel's Edison, Galileo, and many others. So the interface that provided could be both digital and analog, as I mentioned. Digital sensor could be like push button. Analog could be potentiometer, temperature sensor, pressure, weight sensor. So I look around on the internet and found this. Someone tried to put a small cluster of computer which composed of Intel Edisons together. So this is we call it a system on chip. So you put a couple of those together, wire them up, and you can have a small cluster to do your data processing running Linux. So let's look at what enable the Internet of Things. So we see some RFID chip that I mentioned before, near field communications. We see optical tags or QR code that you can use camera to read the code and then send data along. It's kind of like remote sensing in a way, right? The advancement of Bluetooth low energy, Bluetooth 4, consume really little energy when connect to devices. We have some other low energy wireless IP network, ZigBee technology for communicating between devices and can propagate the data from device to device. In case that you don't have network available, you can have a bunch of ZigBee device, in the field, and it will start to propagate data over. Some other interesting technologies like wireless power become available, so you can walk around in the room and then you get your smartphone charged, right, without connecting the wire. That's are pretty exciting technologies. So in terms of landscape, we observing a lot of IoT platform providers start jumping into the fields. For example, Microsoft Azure IoT Hub, Amazon AWS IoT, AT&T, IBM Watson, Verizon, Cisco, big players in the field. It doesn't mean that these are the only players. There are a lot more players in the field. This is an example of players in these IoT fields. So the field has been pretty much level, and anybody can come up, right? If you learn about technology, you learn how to put together devices, learn how to program, learn how to put it on a map, then you could be one of the players. So look at the application and market. So this is the 2020 forecast that has been changing over the last few years. We used to say that last year the forecast came out 50 billion connected devices by 2020. This year came out 75 billion. So you could see the rate of change is, I don't know if unpredictable, but it's accelerating. So on this chart, by 2020, we're going to have 4 billion connected people, $4 trillion in revenue or opportunities, 25 million applications, 25 billion embedded intelligent system, 50 trillion gigabyte of data are going to be communicating over the internet. So I don't know which part you want to be with. One of these get fraction of percentage, you probably get making some money. So some surveys came out asking what kind of device likely to be connected or people concerned about having it connected. So this chart showing one is the home security camera, house door, car, TV, you can imagine heating system, oven. I don't know if I want to connect my oven, probably. In terms of applications, there are a lot of applications for IoT, but we pick out a few that are more relevant to GIS. The number one is smart cities. Even smart nations, if you talk to Singapore people, they call smart nation, they're not smart cities, right? The entire nation project or initiative. We have environmental monitoring, infrastructure management, energy, retail, you can name quite a few in here. Pretty familiar, transportation, buildings, agriculture, and wearable. So I'm going to get into some details about some of these applications on the list, like smart cities. To become a smart city, so what could tell which city is going to be called smart cities? So there's a group of people that put together some indicators, try to classify which city can be categorized as smart. So you could look at all these indicators if you're working in that domain. So you have to look at, do we have smart people in the city? We have smart economy, we have smart environment, smart government, smart living, smart mobilities, and they are subcategories inside of those. For example, if we talk about information and communication technologies, these are all the aspects that see the call out from the ICT, right? We have network access, services, and information platforms, information security and privacy, electromagnetic fields, and I believe there are more. So some of these, I think this PowerPoint showing the stacks or multi-layer architecture for the smart cities. So this coming out from Cisco, try to show us the stack of technologies. Application could be smart parking, smart lighting, waste management, environment monitoring, and you could see what should be at the basis of this multi-layer architecture. I provide a reference there. You can read the article. So I went to a number of hackathons myself and involved in some of the IoT hackathon projects. Typically, 36 to 48 hours, started on Fridays and last until Sunday. So one of my projects was to create a smart trash can. I work with another 2 young programmers. So we used Intel Edison, put together, bring a trash can, plastic trash can, and then connect with a few sensors that you see on the list. So these sensors, we have LED, and we have temperature sensors. We have GPS to tell the position or location of the trash can. We have ultrasonic sensor that can detect if the trash can getting full or not full. You could see on the upper right that I put some cardboard paper and then stick some sensor on it on top of the trash can, and then the ultrasonic sensor that you see, like the 2 cylinders, are pointing to the level of the top of the trash can, so that when someone throw paper and full, right, getting full, is then out data that say I'm full, come collecting the trash. So the idea was for the city, if they know that, okay, the trash getting full here, they can direct the trash truck to collect it instead of driving as regular pattern this day. Sometimes the trash not getting full, but while you're driving there, right, wasting the gas. But if you know where it's getting full, you can just go there and pick it or plan the route better, saving some money. And we also have tilt sensor put on that trash can, so if the trash can get knocked down, we know it cannot serve you anymore, so we have to go and fix it, put it upright. Pretty interesting. So smart trash can is not just a fun project for hackathon, but in reality, for example, in the East Coast, Chicago, Boston, Philadelphia, they use the so-called big belly, even they call smart belly, trash can. On the top of the bin, you see solar power. So this smart trash can do compaction as well. So it's compact the trash. It's said to be more, I think, 5 to 10 times more efficient than just typical trash can that getting full quickly, but this one compacted so you can collect more trash. This one costs about $3,700 as opposed to your typical wire mesh trash, $100. Anyway, I don't know how much city will save money. From the statistic, I think Philadelphia deployed 12,000 of these cans. 12,000, so millions of dollars. So look at Smart City Dashboard. So this is from Cisco again, kind of gives some indication of, know what, kind of situation we are in. You see water quality, air quality, traffic congestion, and anything else. So, well, you look at this dashboard, and we can use our operation dashboard, probably come close to this. The other application, connected car or smart transit. So big vendors also jump into this. You see Nissan, Tesla, GM, Ford, BMW jump into this connected car. And I learned that here got bought by one of these car companies. So you can see that mappings and geospatial data has become very important for connected car applications. Also, we start seeing a lot of sensors connect to your OBD2 port. In every car, after 1980, I believe, have this OBD port available that you can connect to the computer, and you will read all kind of information from your car: fuel level, temperature, torque, steering angle, everything you can read out from that OBD port. And then you can send it over the internet somewhere, and you can do detection of the health of the vehicles. You can detect the heart rate, you can detect fuel consumption, and so on and so forth. Players in the connected car arena, this is an example of the list that people put together. So move on to the wearable. So this is also an exciting one. I have one on my wrist today. It's a Samsung smartwatch, and Josh has one that he's going to show it off today with the IoT demos. I'm not going to show mine, so not competing with him. So on this chart, there's a survey come out saying where would you want to wear or to have the sensors device on your clothing or on your body. So 29% say clip it on the clothing. 28% say on the wrist. 15% say embedded into the garment. 12% say put on jewelry. 4%, let's go back in. So 4% say on the contact lenses, 3% say tattoos on my skin. Interesting. I happened to watch a movie called In Time, which came out in 2011. Interestingly, this movie used a lot of embedded device into the body. There's a clock embedded onto your arm, right? And at age of 25, you stop aging in the movie, okay? But after 25, you can only live one more year. So you got to work to earn the credit to extend your life. You don't work, your clock ran out and you die. And people can exchange time to their wrist. So let's say I'm so rich, I have 10,000 years, I can give you 100 years, I guess, do it like an NFC, field communication, and just give you some more time so you can live longer. An interesting movie. So we categorize the wearable. So when people also put together this chart, you can see that they categorize by sectors, by functions, and products. So in terms of sectors, you can see security and safety, medical, wellness, sport and fitness, lifestyle, communication, and many others. So look at the wearable example of how that embedded into the garment. So you can see that they embed the circuitry onto the garment itself. And you can watch that, you can put in the dryers, they're gonna last, through those washing machine, and don't spin it too hard. These are embedded wiring and sensors that can be waterproof. And then there must be some sort of hub on the body to collect the information from sensors from the garment and send to the internet. So this is how it may work. One of that help could be smartphones, and we have back-end servers that can do detection and alerting. So I'm gonna show the first demo. So they're gonna be sensor on smartphones. So on smartphone, we are pretty much a walking sensor. We have a bunch of sensors on a smartphone. What I'm gonna do is, I have a small application, Android application here, that using the accelerometers. So if I move too quick, it's gonna send information over the internet to the backend GeoEvent server. Okay, let me get to that. So if I just, let me see if I can show the, so this is the backend GeoEvent running on the Amazon. So if I move slowly, I hope that, you see the counter start increasing, right? Oh, you don't see it? Okay, well, never mind, let's see this.
Hi Morakot. Fall incident detected.
So if I check it, I have an application on this machine that connect to GeoEvent on Amazon, somewhere else. And when I move really fast, simulating that I fall, It's going to send information over to the internet, to
Hi
GeoEvent.
Morakot. Glad you are okay.
Yeah,
Take care.
It will detect the range of accelerometer values and then do the filter and then send information. And assuming that I'm okay, then I touch the button on the phone just to say that I'm okay. It will send a different information to that applications. See,
Hi Morakot.
okay.
Fall incident detected. Are you okay?
Try that again.
Hi Morakot. Glad you are okay. Take care.
All right. Okay, let me take this one now.
I can make it.
Should we switch it?
Yeah.
Okay. So Josh's going to take over from this point.
Cool.
Take on, Josh.
Thanks, Morakot. Now you guys can hear me. Thank you, Morakot. So one of the areas that I've seen... Can you turn yours off? Sorry about that. So one of the areas we're seeing a lot of growth in the... I'm going to back away. Getting some kind of feedback here. We're seeing a lot of growth in the connected environment. And when we're talking about connected environments, these are sensors in the ground. These are sensors on water sensors. There's a number of sensors here. You see some examples from Valarum. They provided us here. And these are things that are allowing us to constantly record information about the environment we're in. You may be surprised to know that actually probably the majority of the people in this room have some sort of smart or connected technology in their homes already, whether this is appliance monitoring, looking at the usage of your power usage, security systems, your HVAC controls, something like a smart thermostat. When do I want it to turn on? Do I turn it on at a certain temperature? Do I have a programmable thing? Do I have an app through my phone that lets me turn these things on? Any kind of environmental sensor that allows you to then have a computer or a smart interface for this. Oh, I'm kicking out. Lost my PowerPoint. So for anyone that attended one of our sessions at UC last year, we gave a demo with some of the Philips technology. So we were doing some sensor information coming in and showing it with how the color would change through a Philips light bulb. Those have been around for a number of years. Also things like some of the Nest smart thermostats at homes. These are a way a number of people are wanting to get into, losing it again? Okay, now I can get a little closer, I can see. So there's a number of ways that you can take some of that technology. If you're willing to do some of the hardware changes in your home, you can implement some of these kinds of automation technology. Also, there's a new company it's still kind of in a startup phase right now. It's called Sense. And what Sense does is actually it's a device that hooks into your electrical panel, and it's using pattern recognition software. So 1 million times a second, it's monitoring both the draw of power and the flow of power going out of your house, and it identifies devices that are running in your house. So it knows the kind of power signature of a refrigerator. It knows how much power is typically used when the compressor comes on, when it's just in a normal running phase, and it can differentiate that from, say, a toaster or a hairdryer. And it gets in this learning mode where without having other than the electrician wiring it in the first time, you're not having to have an individual sensor on each outlet in your house. So it allows for some really useful insight into the environment and what's going on in your home. Now, for people that want kind of less invasive automation, they're interested in bringing in, there are some of these assistant devices. Amazon has like the Echo and the Dot. They also have the dash button there, like you see the little Tide button. These are really cool. These are devices that they're IoT, they're devices, but they're tied to a specific product on Amazon.com. So in this case, you'd stick it on your dishwasher and it runs over, washing machine. You stick it on there, and when you're out of detergent, you press that button and it automatically ties to your Amazon account and orders more of that product and ships it to your house. And there's several hundred of these products. You can stick them over the house. We bought a handful of them. We stuck them in the drawer for, like, my daughter, granola bars. So there's a kind of granola bar. She packs her lunch every day. If she runs out, she presses the button. It orders them for us automatically. So it's pretty cool, neat way to get into stuff. There's also Google's getting into this with their Google Home device, another kind of automation system. And there's a new one that's pretty cool called Mycroft, which is all open sourced. So it's kind of competing with some of the big boys in the market. But I think there's some exciting stuff coming out of that as well. So how does all this technology impact GIS? We're at a conference here. We want to learn about how this is affecting GIS. It's not just about, making our homes connected. So let's kind of take a look at that. So when we're talking about some of the Internet of Things, we're really talking about real-time GIS. And what's essential when you're working with these IoT devices is having some sort of spatial reasoning. Having the improved connectivity and reduced cost of some of these sensors allows us to put sensors in more locations. You're able to get a better picture of the environment you're trying to analyze, whether it's a home or a warehouse or a field. You having these devices in more places allows us to get better and more meaningful patterns about what is occurring, being able to identify that. And using some of the technology that we have at Esri, we're able to act on that information coming in, do some pattern analysis, do some filtering, some processing on it, and being able to send that out in a usable format. But the data we're talking about when we're seeing data coming in from these sensors, this is observational data. So it's a little bit different from maybe some other kinds of data sources in that all the information coming through is going to have potentially both a space element, some sort of geography, and a time element. So we're able to go back and play through some of these times, and we're able to see what was captured at a certain point. Also, one of the benefits and the important part with any kind of these IoT devices is being able to identify a unique track. So we want to make sure that the devices we're looking at, if we're getting an update once a minute, we want to make sure that we're looking which device it was coming from. So we're able to differentiate that over time. And then we can go back and play these things back over time, like a VCR. You can pause it, you can rewind it, you can stop it, being able to look at these kind of snapshots in time and being able to analyze what occurred. The way we do that from Esri predominantly is with our GeoEvent Server. That's our primary real-time product. And that's a part of our ArcGIS enterprise. So I know Sud was talking about this morning when he was giving the overview of the platform. GeoEvent Server is a functional server. Its primary role is to ingest high volume data, to be able to analyze that data while it's coming in, to be able to store that data, and to be able to visualize that. And we're able to ingest it from a number of sources. You see some examples here from planes and trucks and ships. These are AVL sources. We're actually tracking the moving object. But we're also talking about just that sensor data. Hopefully, if you have stream sensors in there, those devices themselves aren't moving, but they're constantly sending live streams of data that we're going to be updating about. From this data coming in, we're able to both analyze it, being able to do analysis on looking for certain sensors. So if we have a stream sensor that's set to maybe do a gauge height, how much water, what's the level, we want to be able to put alerts on there. So maybe if the water level goes up 2 feet, we don't care. If it goes up 10 feet over a certain amount of time, now we want to know. Now we want to send email alerts out. We want to send out text messages. We want to be able to notify people of some sort of condition that's occurring. So now that we have a little bit more understanding of what we're doing on the back end, and we'll dig into that a little bit deeper, I want to kick it back to Morakot to explain on his demo. This is what we tried to show you earlier in the other screen.
Right, so
you're on 4, 3.
That's okay. You can keep it there.
Oh, all right, fine.
Yeah, keep it there.
Easy enough to do.
Yeah. So yeah, this was the interface on GeoEvent that I wanted to show you earlier. So we have the logic diagram that the green box is where it's reading the data or receiving data from smartphones in JSON format. And after that, it will push the data through the pipeline. The first one would be a filter. So there are 2 filters here. The first filter is if the accelerator values more than some threshold value, then we process on the first branch, which forming speech to be sent to the output to TCP. And then my application is sitting on a remote machine that connects to that TCP. It's a text-to-speech. It receives the text from the TCP and then turn the text into speech and speak out on this computer and announce it, right? And on the second branch, when I touch the button, so it say, okay, button okay, it's sent, so I'm okay. That's why it's saying, Morakot, are you okay with that? So that pretty much is, yeah. Back to Josh.
That's better. Thank you, Josh and Mocha. Well, my demo today is going to be using a Raspberry Pi as a flight sensor. So before I run the demo, I would like to show you this diagram of an IoT architecture. There are many different shapes and forms of IoT solutions, and the architectures may be different. But this diagram shows the basic elements that are involved in most IoT solutions. Every time I build an IoT demo, I get a new appreciation of this diagram. At the very bottom, we have the sensors, actuators, and the displays. They are the edge devices that are responsible for communicating with the outside world. Then we have the application framework and the service gateway. Their functions are to manage the hardwares and softwares running at the edge and connect the edge devices to the cloud. Both of these layers typically run on the IoT devices. The IoT integration platform on cloud functions as a central collection and the dissemination point of IoT data. You can view it as a real-time event hub or IoT hub. In fact, Amazon and Azure, they both have their own IoT hubs that are running on their clouds. For this demo, we deployed our own IoT hub, which is a MQTT broker. You can use any IoT hubs as long as your service gateway and business application support it. The business application layer is where the GeoEvent server fits in. It ingests data from the IoT integration platform. It performs real-time analysis. It can generate notifications or alerts, and it can also write commands back to the IoT integration platform to instruct the devices to perform certain tasks, such as turning on a light or changing the color of light bulbs. If you have been to this session in the previous years, you may have seen our demos that match very closely to this architecture. We had a Raspberry Pi with a temperature sensor and another Raspberry Pi with an LED light. In another instance, it was the Philips Hue light bulb instead of the second Raspberry Pi. The temperature data is published to the cloud, and GeoEvent is used to read the temperature data from the integration platform on the cloud and determine when to turn the LED light on or change the color of the Philips light bulb. This year, we're going to change things a little bit. We're going to use our Raspberry Pi again, but instead of catching the temperature reading, we will collect flight data through the radio signals that they transmit. We put the data captured by this IoT device on a web map. And here's a little bit of background. Modern airplanes are equipped with the ADS-B transponders. ADS-B stands for Automatic Dependent Surveillance Broadcast. It's a surveillance technology in which an aircraft determines its position via satellite positioning and periodically broadcasts it, enabling it to be tracked. The information can be received by air traffic control ground station as a replacement for their secondary radar. It can also be received by other aircraft to provide situational awareness and allow self-separation. So the ADS-B broadcasts at a frequency of 1090 megahertz. An RTL SDR radio receiver can receive the signal. The SDR stands for software-defined radio. With proper software, we can decode the signal into a series of events. So my knowledge about avionics ends about here. Now we have the flight info captured on the Raspberry Pi. We'll again use Cura, which is a framework that runs on those IoT devices, and a custom module that we created to send data to the integration platform from the Raspberry Pi. So we also set up our GeoEvent server to subscribe to the topics on the MQTT broker. And whenever the topic receives a new flight info, the GeoEvent server will use it to update the feature service. So finally, we create a web map to show the flight and their trails. So in the previous slide, we have talked about a number of terminologies outside GeoEvent and ArcGIS. So it all boils down to these three that you need to know if you want to build a similar project. So MQTT is a protocol that is popular in the Internet of Things world because it's lightweight and a low bandwidth requirement. And it employs a publish-subscribe model. Cura is an application framework that allows IoT devices to communicate with underlying hardware, such as sensors and actuators, and with the IoT integration platform, such as the MQTT broker. And PAHO is a library that facilitates the communication with the MQTT protocol. It comes with different flavors. We used its Java-based library in our custom transport to publish and subscribe data from MQTT broker. So this is the GeoEvent service that takes the data from the MQTT broker and put it in feature layers that can be displayed on the map. We have two MQTT inputs. The only difference is that they subscribe to two different topics. These inputs use a custom transport and a custom adapter. Custom connector, I should say. The custom MQTT transport is in our gallery. If you search for MQTT for GeoEvent, you'll find it in GitHub. I have an entire session tomorrow that talks about how to create custom connectors with GeoEvent SDK, and we'll deep dive into the input, the custom connectors, and the custom transport during that session. So if you are interested, please join me in that session. So the role of an input is to get the data and convert the data into GeoEvents. We then send these GeoEvents to a field mapper processor. This is an out-of-the-box processor. We use it to just add a timestamp to each GeoEvent. And then we have two outputs. One is to update the feature layer, which contains the last position of an airplane. And the other is to add a feature output, which we used to show the flight trails. We enabled the auto-delete function on these two outputs so that we can remove a flight if it has not been updated for a while, and then to keep the trails to a certain length. So this is what the device looks like in real life. I have two of those identical devices. One of them is right here. I have an antenna here in the Raspberry Pi and a dongle that receives the radio signals. I don't know how much signal it can receive in this enclosed room. So that is why I left one in my office by the window. And the picture on the right shows the plane. This single device can track. It also shows the data that we captured from the radio signal. In radio communication, the antenna and the placement of it is very important, but it's beyond the scope of this demo. So now let's take a look at what the live map looks like. I hope there are flights that we're tracking. So it all varies. These are the flights that these two sensors are tracking at this moment. When we started the demo, there wasn't any. And then about 5 minutes ago, there was quite a few, and right now there are only 3. So let me play a short video to show you that what it could look like. And this is a video I captured this morning after I got here in Palm Springs. And so basically, before I play it, I just show you the location of these two sensors. One is here, and the other one is right here. So I'm going to play the video, and I know we're running out of time, so I'm going to play it really fast. Wait. Okay. This is 5 times the normal speed, and you can see the airplanes are moving. The web map updates once every 6 seconds, and it's if I accelerate it by 5 times, then it's almost like a 1 second every second it updates once. So that's pretty much it with this demo. And then one more slide, which is the link to the repo. I have a repo that on GitHub that talks about how to set this demo up. And if you're interested, you can follow these instructions and take a look and set up your own project. And then I also have this live web map. And if you look at it at different time, you may see different airplanes, different number of airplanes. So with that, I'm turning back to Josh.
Just to add to Ming, the device that you see here, in the past, I used to buy this for $600, but it's a big one. This time you buy it for $30, right? 5 years later.
Cool. Thanks, guys. So for our last demos, we're going to touch briefly on elements of both what Morakot and Ming showed. And we're going to be looking at the Amazon Web Service IoT button. So some of the feedback that I got after our last demo, we did this with UC last year, was that this is really cool technology, but for someone that's the average consumer that wants to jump in and try some of it, they don't know how to build their own computers, they don't necessarily know that, I just want to play with something. So what we're going to be playing with today is the Amazon IoT button. These are like 20 bucks off Amazon. I got a handful of them. Adam bought a couple, and then Morakot bought some too. They're a lot of fun. The nice thing is they are fully programmable. So these are very similar looking and function to the dash buttons I mentioned earlier. But unlike those that are tied to a specific product, these actually give you full control through the AWS Lambda interface. You can program them to do whatever you want. So that's the interface we're going to be working with today. We're going to be using the Amazon IoT Hub. That's kind of the castle-looking one. We're going to be pushing data out to the Lambda interface, which is their programming interface within Amazon. And finally, it's going to go to the if this, then that, if maker channel. So we're going to be able to send it out to do some stuff. So to get started, for those of you that want to try and follow along or do this later from the slide decks, there are 3 requirements. The first is that you're going to have to need an AWS account for the IoT. They do have a free account. It's like a 12-year free account, so it's a pretty cool way to get started with that. And if you do choose to opt for a payment-based plan later, whatever you design, you're not having to rebuild it. It just carries over with everything you built from their free plan. You also will need to create an account at the IFTTT website. Again, that's also a free account. And once you're within that, you're going to want to sign up for the Maker channel. That's one of their developer channels. And it'll walk you through this process pretty easily when you create an account with that. But here's the websites on there. So those of you that want to follow along later. So as with most things in life, there are easy ways to do things and hard ways to do things. I happen to be a fan of the easy way whenever possible. So rather than configuring the devices entirely within the Amazon interface, they've actually created an app for smartphones that'll do a lot of the programming for you. So we're going to kind of follow through that. I'll talk through what's happening here. So when you first hook up the device, you sign into ArcGIS to the AWS, and it's going to quickly link through. Wow, that's playing a lot faster than I thought it would. Let me pause this here just a second. So when you first log in, you'll put your credentials, and it'll say, hey, there's no devices connected yet. You have 2 options. You can either set up the AWS button, or you can buy a button if you don't have one. So then I'm going to say, this is basically the agreement page. Obviously, I read it a little too quickly because it just sped through there really fast, but you should, of course, read through the usage terms. Then what it's going to want you to do, the downside of videos. It's going to want you to put in the device ID. You can manually enter it, or you can do like I did, and you can actually just take a picture of the box, and it'll automatically pull in the device ID for you. You can then enter a user-friendly name. So in this case, it's called an IoT button 1. And go ahead and register the button. And what this is doing on the back end is it's registering your AWS IoT thing. It's creating the primary key. It's setting up all the security necessary for you. Then the next thing it wants you to do is to actually configure your device with your local Wi-Fi. So what you'll do is you'll press and hold the button for 6 seconds. It'll then create its own local Wi-Fi network that you'll log into, set it to use the credentials that you want. The first part I'm entering now was the credentials for that specific device, because you're going to log onto that network. Then you'll come back into the app, and then from the app you'll tell it which network you want to use. So in this case, this is one I did back within our office. So you'll see in a second the screen will kind of fuzz out because it's going to have me prompt my Wi-Fi credentials for our office. So I picked the Esri internal network. So, you know, Apple's nice enough to show you on the screen while you're typing it. We're going to use the trigger, the IFTT maker channel. And what you're going to need to do is when you're setting up that connection earlier, connecting that channel, it's going to give you an API code that's a key specifically for that connection. And I know I went through it really fast, but if you were to get that, it walks you through each step. It kind of tells you what you need to enter here, click it, and put it in. But I know for time, I wanted to kind of show you guys what's going on. So behind the scenes, for people that are watching the video afterwards, and for you guys that are wanting to know a little bit more about it, when we're programming it through the app, what it's doing on the back end is this is the sample code that it's setting up within Lambda. The important part out of all this is the first part, which is actually the payload that's being sent when you click the button. It's going to send a serial number, battery voltage information, and one of 3 different types of clicks. So it's either going to be a single click, a double click, or if you hold it down for 3 seconds, it's going to send a long type. Now when that sends it to Maker, what it's sending is it's sending the serial number dash click type. So this is really important because when we're setting this up on the IFTTT website, we need to identify what event to be looking for. So we'll play through this as well. And when you go within to the IFT website, you'll first need to do on the if side, what do you want the source to come from? And there's a few hundred different potential services that you can use on the input side. I'm just scrolling through some here. There's different ones for Best Buy that's come up second. You could have it look for a certain price. So if you've been holding off buying an Xbox for years like I have, you could have it set in a certain price. If Best Buy tomorrow sets that price, you can be notified about that. You can have it follow certain Reddit threads. You can also set it up to your GitHub account. So if someone pushes an issue, you can have it alert you and notify you of that. So it's going to scroll for just another second or so and then jump back up here for us. One we're concerned about on the input side is the Maker channel. And that is specific for their developers, but it's really nice. So what we've set up here is we're going to receive a web request. So this is sending the web request from the Amazon IoT Hub. And we need to give it an event name. So the event name in this case is the device ID plus the type of message we're going to be sending it. So we're going to be sending, in this case, a single click message. So it's going to have the device ID dash single, create the trigger. Then we need to figure out what we're going to do with that. So just like we had quite a few on the input side, on the if side, on the that side, we have a lot of options as well. The one we're going to use just for simplicity here is just an SMS text message. By default, it's going to send this block here that says an event named, and then whatever type click you did, out to the Maker service. But for simplicity's sake, just to show you that we can do something, just have it say you pressed a button. Good job. Kind of our IoT hello world test here. So to actually see this in action, this is a video, but I press the button. Takes about 20 seconds or so. And we'll see that I got the text message. You pressed a button. Good job. So that's coming through. Give this just a moment here. Now the other one we also set up was a second one that had to do with a double type. Oops, excuse me.
Hello, Josh. We hope you are enjoying your visit to Palm Springs and the Esri Developers Summit. Message brought to you by...
So I got cut off there at the end, but so I pressed the button twice that time and it called me. So it kind of interrupted my PowerPoint presentation to let me know I was getting a call. The third type that I also set up, because I mentioned we had single, double, and long. The third type is actually sending a post request to a REST endpoint that we set up. So we have GeoEvent Server listening for JSON on a REST endpoint. And what we have set up there is that basic input coming through is sending an airport identification code. So in this case, I had it do KCXP, so that's the Carson City airport. Within GeoEvent, we have this going through a field enricher where it's joining it to a feature service that includes METAR weather station data. So when we press the button, it sends the airport identification code, which is then in real time joining it to a weather station information. So the output of that is going to have live information that then goes through a series of field calculators to kind of clean up the message a little bit, make it into a little more human readable format, or I should say machine readable, because we're going to run it through the text-to-speech program that Morakot showed. So we'll let this play.
Hello, Josh. The following information is for Carson City, Nevada, United States of America. The current temperature is 26.6 degrees Fahrenheit. There are a few clouds at 550 meters AGL, scattered clouds at 700 meters AGL, broken clouds at 850 meters AGL with light snow.
Now, obviously, that was a few days ago when they were getting some snow there. It looks a little nicer now, but with that, I'm going to hand it back over to Morakot.
All right, thank you, Josh and Ming. So we come to the last section of these presentations. So we're showing some of the nice demos, and now talking about how we get the data in, how do we storing it for further processing. So from the input side of GeoEvent, these are lists of out of the box and all the gallery items and even community supported or contributed. So you can see that we have a range of connectors for you. So connector is protocols, transport, and data formats. So we support JSON, XML, CSV, and many others binary that might become custom using our SDK to develop that. So for output, we can also send data from GeoEvent Server to different sources. We can update feature services. We can put it into the big data store. We can send to MQTT. We can send to text-to-speech, whatever you can see it. And then you see at the enterprise level, we have big data in real time. We have spatial temporal big data that can store a lot of data for you. Millions and millions of records, which is very powerful. You can query the data back, millions of records in a few seconds. Okay? For database, if you pass multi-millions, maybe you have to sit for 10, 15 minutes. But for the technology we put into the big data, using Elasticsearch, we can put it back in just a few seconds. So this allows you to do continuous analytics using GeoAnalytics Server, which is running on Spark. And that works together with the big data store. So you can see the IoT come in to the left, and then big data to the right, and then you have GeoAnalytics and our storage in between. So this kind of summarizes the big architecture of our real times and big data and also analytics. You can get more detail in session here. Don't worry about if I just write through that because we don't have enough time. So the next step that Adam has been working on is really big, massive scale. So if you want to address the scale of smart city, smart nation, we are building a new, would say, architect or products for that. And this is still in the work. This will use a lot of computing powers, so it will be a managed service. If you want 3 terabyte of RAM and 60 terabyte of SSD and 80 nodes. You can buy computers, it's very hard to buy computers with that computing powers. So mostly they're going to be running through some sort of cloud providers, allow you to spin up VMs and assign computing units in containerization manners, so you can have all those applications deployed on multiple nodes and work together in a distributed computing and parallel manner. So it will speed up consumption of a lot of data, IoT data, and also when you want to do analytics, that will empower it. So for detail, follow Adam's sitting here in his session. So I'm going to leave that with a summary. We have shown that we have Internet of Things that will be able to addressed by our ArcGIS platforms, and more data from IoT will just be coming and increasing, so be ready for that. Also data will keep piling up in your storage, waiting for you to analyze and pull out patterns for predictions and historical analysis. So get ready for that. After session for GeoEvent, this is a list. So we have been very active in GeoEvent and real time. So these are sessions that if you want to dive into more detail, just follow those sessions. And if you can fill the survey for us, that will help us determine if we can be here again next year. So thank you very much, everybody. Thank you.